on X-ray spectral analysis. And it's a pleasure to have Johannes Buchner as a lecturer for this particular topic. Johannes completed his PhD in 2015 at the Max Planck Institute for Extraterrestrial Physics in Munich. And his thesis was on Asian demographics. And after his PhD, he moved on to Chile and the Católica University, where he stayed there for 3 years with a fellowship from the Chilean Foundation of Technology and Science. And since then, after this postdoc, he is back at MP, he's back at Max Planck in Munich, working on a new mission, which is a new X-ray mission, which is called eROSITA. Now, Johannes combines astronomy with statistics, and as part of his astrophysical research, he has developed a lot of statistical tools and a lot of analysis tools that are widely used by the community. The one relevant to this particular lecture is called BXA, it's Bayesian X-ray Spectral Analysis Tool. Yeah, so he will be talking about that and demonstrating the art of X-ray spectral analysis using Bayesian statistics. So I give the floor to you, Johannes, and thank you very much for accepting the invitation.
Oh, thank you very much for the nice introduction. Welcome to the tutorial. Thanks for having me as a lecturer. Yeah, I just wanted to say a few words about the lecture and the format that I thought we would go through. So I think I will basically cover a motivation of why X-rays are interesting. And of course, many topics I cannot cover, like very high energies and timing analysis and imaging analysis. I will just focus on spectral analysis. And I think this lecture also nicely ties in with what you heard last week about the Bayesian inference. And in that framework, let's look at the outline of this lecture. So you heard all about Bayes' theorem with the prior of some parameters, the likelihood, the evidence, and the posterior. And so in the first block, which is this session, I would introduce first why X-rays are interesting, why do we study them, how are they detected, how do the detectors work. And this is very important if you do some analysis that you really understand what the process is. And if you do a PhD thesis, you'll be asked to write a short paragraph about how the mission works, how the detection mechanism works. I'll cover a little bit about background, either in this session or the next session. I don't know yet how the time goes. But in the end, I'll describe how this likelihood is constructed in the case of X-ray analysis. So basically how we imagine the data being produced. And then in the second block, we'll use that likelihood combined with a prior to do posterior analysis. So first block will be on the likelihood, second block will be on the posterior, so posterior of parameters. We want to constrain parameters, we want to say this luminosity is between this value and that value with high probability, something like that. And we want to differentiate models. So model comparison, which mechanism, which physical mechanism is active. And for that, we'll use the evidence in Bayesian model comparison. And yeah, potentially I'll talk about how to deal with backgrounds. The format will be, I'll give a bit of a lecture, maybe for an hour. And then I will, if it works out with the timing, I will give you the first tutorial, which is just playing around with the likelihood essentially in one of the frameworks that you hopefully were able to install. If you weren't, please help each other, share screen in the breakout rooms. And yeah, if you didn't manage, it's also not the end of the world. I'll demo in the end what should have done, or I'll ask a volunteer. If you have any questions or you got confused, please either yell or write the question in the chat, and I'll keep an eye, and Helen and Antonis will also keep an eye on the chat, and I'll try to reiterate or come back and answer these questions. So just ask the questions in any way, but I will also make some stops along the way for you to ask questions. Yeah, I've understood from talking to Helen and Antonis that some of you are more from the theory side, some have experience already from X-rays, and some are just in general interested in AGN, for example. So I'll try to sort of cover all of these backgrounds. The other thing you should keep in mind is, okay, this is fairly narrow topic, X-ray spectral analysis, but if you do any other analysis, you can still learn lessons here about how to do Bayesian inference in practice, even if you have a completely different problem. Okay, are there any questions right now about the format or anything that is confusing? If not, then I would just jump right into why we are interested in X-rays. And some of these slides are adapted from Johan Wilms, and he has very nice lectures online that I also sent you links to. So here is a nice cartoon of the upcoming Athena science objectives. So Athena is a mission to be launched in a few years. It's the next very large mission. And here are some of the mechanisms or objects in the universe that we can study with X-rays. And well, starting at the bottom, you have hot plasmas, so electrons that are very hot, producing high energy radiation. Also, another hot plasma is these galaxy clusters that you see here, where you have gas that is very thin and cannot cool, reaches millions of kelvins, and this radiates in the X-rays. And so you can study these gases, their temperature in the X-rays, and trace out most of the mass in these galaxy clusters with the X-ray. Another phenomenon that is important in X-rays are compact objects. So black holes, which have very violent and energetic environments, accretion disks, which produce X-rays in their vicinity. And I mean, they are stellar black holes, there are neutron stars, there are pulsars that you see here. All of these are very interesting because they probe extreme physics, and with the X-rays that are produced very close to these objects, we can probe these physical environments. And so it is very interesting for a variety of reasons to use X-rays to go to these extremely hot and extremely energetic phenomena. So just some examples. I mean, of course, there are many more. Hot plasmas and compact objects are some of the objects that we're interested in. So you can learn about the temperatures, the turbulence of these hot plasmas, or the accretion rate, the spin of these compact objects. And here are some example models that you might be able to use in these contexts if you think about spectral analysis. So here's sort of like black bodies, but with lines on top. And here the most primitive model is, of course, well, are power laws, but of course the reality is more complicated than power laws. Okay, so why do we have why don't we have X-ray observatories on ground? Well, if you look at the how the atmosphere is able to absorb various types of radiation, that's shown here in the colors. You see that the X-rays penetrate not very deep into the atmosphere. Basically, you only have the visible light and the radio. So the reason for that is the gas in the atmosphere has photoelectric absorption, which goes with the energy to the -3, so the energy of the photon. So the higher you go so the photoelectric effect is basically you have an atom, a photon comes in and kicks out one of the electrons and gets absorbed. And so it doesn't go through. And for that reason, we have to go to space to observe the X-rays, go past this atmosphere, and that's why we need to use satellites in X-rays or balloons back in the day. So what's the present status of the X-ray satellite landscape? Two important missions that dominated X-ray astronomy for the last 2 decades are XMM Newton and Chandra. Chandra is having quite a bit of issues now. A new mission is New Star, which goes to higher energies, and here listed a whole bunch of missions, other missions that are active that you should know about. Spectrum Röntgen Gamma is the satellite that hosts eROSITA, the mission I'm primarily working on. So at the moment we have actually a golden age of X-ray and gamma ray astronomy with a lot of missions online, and you can see that here in the timeline as well. This sort of radio and optical, and here is the X-rays. So at the moment we have quite a number of missions, but then starting at 2023 or 5, some of these will be die out, so you might be wondering what's going to happen soon in X-ray astronomy. But actually, there are quite a few missions coming up, and at after a while, there's Athena planned in 2032, which will be the sort of the successor to XMM Newton, a very large mission. But there are missions in between that could be very interesting for your research. So how do we detect X-rays? How do we actually measure these X-rays that we're interested in? Well, usually you are interested in focusing the radiation, because otherwise you don't know which X-ray belongs to which object on the sky. So in optical astronomy, you use mirrors made of glass or lenses. This doesn't work in the X-rays because the X-rays just go through the material or land in the glass. And so the only way you can focus X-rays is with relatively low incidence angles. So you basically have an X-ray coming in and it sees a very shallow, at a very shallow angle, a dense grid of atoms, also known as a metal. And with these shallow angles, you are able to reflect it. And this has basically to do with Snell's law and the energy dependence of the photoelectric effect. And so in X-rays, we use the Voltaire telescope design, which uses these shallow angles, for example, here with a paraboloid and a hyperboloid, so two surfaces, so double reflection, to focus parallel rays coming in onto a detector surface. This is relatively inefficient because many X-rays still are not being reflected, and because we have the double reflection. So actually the collecting area of these mirrors is not that great. But it does work. You have to polish these mirrors extremely finely. These are the best mirrors produced, and otherwise you get very poor X-ray images. So you might, and there is a very strong energy dependence because the angle of the reflection is energy dependent. And so we can look at the sensitive area, how effective the mirror is. So this is the effective area of the mirror as a function of energy of the X-rays. This is also described as the ARF, ancillary response file, I think it's called. And here you see, for example, the effective area of a mirror for Athena. And the blue one is the mirror itself, and then there's some coating on top to avoid reflection in the optical and UV. So you see it's very strongly energy dependent, and there are some effects from particular elements that are used in the mirrors as well. Then you focus the X-rays on the detector surface, but now you want to actually detect them and say, hey, we got an X-ray. I will not go into details here, but one way to detect X-rays, or a very important way, is with CCDs. So these are very similar to optical CCDs in principle, or in some principles at least, in that you have an imaging device that can be read out with electronics. In the X-rays, you have the photon come in and it ionizes some region in the detector and produces a cloud of electrons. And that cloud of electrons is then read out with the usual CCD techniques, so shifting the electrons. And the important thing to keep in mind here is that the electron cloud, the number of electrons produced, is proportional to the energy of the X-ray. So for each individual X-ray, in principle, you can reconstruct its energy. And you know its time of arrival and the location on the detector, so location on the sky. Now, when you have an X-ray coming in and making this electron cloud, it can happen that it doesn't just hit one pixel, but several pixels. And these are encoded as grades, so how many pixels on the detector were hit. And this is important to distinguish whether it was actually an X-ray or particle, which might also excite an electron cloud. And for reconstructing the energy, you of course have to put the neighboring pixels together. Now, once you count basically the number of electrons that were detected in this event, and you want to reconstruct the energy of that X-ray, it's actually not unique. So here on the x-axis is the reconstructed energy, and on the y-axis is the actual input energy of one particular instrument, RxTE PCA. And you see that, I mean, ideally you would have a diagonal matrix if you could perfectly reconstruct it, but that's not the case. There are actually cases where you have, for example, a photon of some particular energy, and it primarily makes the electron cloud of its energy, but actually there's also a secondary effect, which has to do with it ionizing the atoms in the CCD. The electrons then can fall back and de-ionize and produce another X-ray. That X-ray has a lower energy, and so you get this secondary line here. And so the reconstruction is not unique, and that means some of the simple techniques that you can get away with in the optical astronomy, you can't get away with in X-rays. And so you need these detector response matrices, RMFs, to forward fold what is going on. I already said you have the, okay, so here on the right you have an optical image, on the left you have an X-ray image. Each point here is very likely an AGN, I would assume. And you see on the right, it looks quite different. Different objects shine in X-rays. But the important thing I want to mention here is that for each X-ray event that you have here, you get its time, its energy, and its position on the sky. So you can do timing, imaging, and spectroscopy, and any combinations of those with the same data set. At the moment, what I will talk here is you have to extract the events at some particular location and basically make a histogram of their energies, and that is a spectrum. Now, I could talk at length about backgrounds, but backgrounds are really important. The detectors capture also cosmic rays, protons that do not go through the mirror. I should have said mirror here. And they make various effects here on the detector that you want to get rid of. Now, once you've observed a particular object and run the pipeline on whatever mission you have, you basically end up with these files, PHA or PI file, which is the spectrum, the number of photons actually detected as a function in various energy channels. This response matrix, which maps energies to channels. The effective area of the mirror, and ideally a spectrum of the background, which could be extracted nearby. And here are some links for where you can download the data in public archives. Now, we talked about the response matrix, so that maps the counts and energies. We talked about the area of the mirror as a function of energy. And now what you have to do is, if you have a particular model for some astrophysical object, so the flux as a function of energy, you have to convolve it with this response, and that then produces counts in a particular channel. So this is sort of the forward folding approach. You basically have a matrix product with your flux vector, and we don't measure this directly. We only measure the convolution. But of course, we're interested in this, and the inversion of this is not directly possible because of the non-diagonal response. And of course, there's also a background. So we measure the number of counts in particular channels, but we are actually interested in the flux density as a function of energy. And we have to know for inverting this, or for trying to learn about this, we have to know about the calibration very well, so the response. So the approach basically is to guess what's the flux as a function of energy. And if you have this, then you can predict how many counts there are in each detector channel. So in your spectrum, you can predict the number of counts. And then you can compare that prediction to the actual number. And this is where the Poisson statistics come in. You make that comparison, that forms the likelihood, and then you modify your guess and you vary this, and basically you vary your likelihood as a function of the parameters of this particular model. Okay, so now all we have to do, well, if your astrophysical model, let's say, is a power law, for simplicity, then you have the normalization and the slope as the parameters. You, for each particular assumption of this slope or normalization, you then get a likelihood value. And so you have basically a surface of these two quantities and the likelihood as the value, and you can explore that surface. That's basically the idea, and to do Bayesian inference on that surface. So let's go into detail on the likelihood of comparing, of comparing the predicted counts and the observed counts. So if you convolve the model through, you have some prediction in energy channel, let's say 3 keV plus minus 0.1 keV. You predict 3.1 events, and you actually observed 5 events. How likely is it that these data were produced with this model? And this is given by the Poisson distribution. So if you have in a particular single spectral bin prediction of lambda 3.1 counts, then this is the probability. Here is plotted for a couple of lambda values, how many counts you should get as a function of their probability. So the counts are integer values. There are no 3.5 photons that you can detect. You can only detect an integer number, positive integer or non-negative integer. The rate, but the rate can be real. It doesn't have to be an integer, right? So you can have a mean that you expect and the actual data scatter around that. It's an asymmetric distribution. That's quite important. It is an integer distribution and it's positive. When you scale lambda up, you see that the shape also changes. And if you, another feature is if you add two Poisson processes together, you add the counts together and you add the lambdas together, you again get a Poisson distribution out. Now, if you subtract two of these distributions, you get a bit of a mess, and that's a scalum distribution. Nobody uses that. It's too difficult to use. But you see it's very different from subtracting two Gaussians where you get a Gaussian again. And actually this is also happening in optical astronomy. If you have relatively faint observations, you get this shot noise and low number of counts. So actually also in optical astronomy, in principle, you should use the Poisson. But for practical reasons, in the high data regime in optical astronomy, people use Gaussian and scale and subtract very easily. And I will show you now why we can't do that in X-ray astronomy. I mean, it's sort of clear already here. First of all, we have single-digit events possibly, but it's also a problem for distributions like this that are asymmetric. Yeah, so the Gaussian can be real and can be negative, but the Poisson is always positive. So what I show here is how this function, how this likelihood, how this Poisson likelihood changes. If you know k events were detected, here one count was detected, how does the likelihood change with the rate? So you don't know the rate, you vary the rate, and this is the likelihood of the Poisson distribution. So if you have one, so in blue I show the Poisson, and in orange I show the Gaussian, assuming a mean of k and I think a square root of k width. And you see, first of all, that the Poisson has a much wider tail to the low counts. Here I can increase also the number of counts to 5. You see it still has this long tail to the low counts and a narrower tail to the high counts. And so it does behave differently. And that's important because if you detect, let's say, 5 counts, if you use a Gaussian distribution, you might think that it cannot be this faint, but the correct answer is with the Poisson distribution, it can actually be this faint and produce many more counts than you would naively expect. And yeah, at some point, these distributions become very similar. Okay, I think I said all of this. Historically, people have used the Gaussian because it's faster to evaluate, but I would not recommend it at all, and it's not really necessary. So what people use then is they say that you have the Gaussian likelihood, which is this formula, and so that's a Poisson. For the Gaussian likelihood, you have this formula, which should be relatively familiar to you. And now we're going to use a magic trick, which is taking the logarithm of this formula and multiplying it by -2. And so we get -2 times the log of the likelihood. And we can write that nicely as 2 lambda, that's this term, and 2k times log lambda and some constants. And for the Gaussian likelihood, we can do the same. And then we get x minus the mean, sigma squared. And that should look sort of familiar to you because that's usually called a chi-square, especially if you sum this over many data points. And for the Poisson, this particular statistic is called C-stat or cache, depending on which constants you attach here. But what you should keep in mind is these are nice names, but they are really just the likelihood multiplied with -2 times the log taken of them. So what people usually do is chi-square minimization or C-stat minimization, but that just means maximizing the likelihood. You should make that connection. Okay, so if you have multiple bins, you already know from yesterday that you can just multiply the likelihoods together. This just means this data has to be fulfilled and this data has to be fulfilled with some particular model prediction. So you just sum up these statistics. And if you have many bins and you do the statistic here on the expected number, the whole process then looks like this. You have some flux vector, which is your model. You convolve it through your matrix, which is the response. You get your predictions in the channels that you can compare to the actual observed counts. Okay, so now we have a likelihood that depends on some physical parameters of your model. That's your model, the response, and maybe also some background that I haven't talked about yet. And that predicts an expected number of counts in each channel. And now you compare that to the actually observed counts, which is this k vector, that's your spectrum that you took. And now you have a nice likelihood, and you can explore and vary those parameters and maybe the model and see how the whole thing behaves. Now, you want probably to go to regions of higher likelihood because the model under these parameters often makes this data, okay? Lower likelihood, this particular model under these parameters less frequently make these data. You should keep in mind here that the likelihood is a probability of data given the parameters, right? It's a distribution of data. It's specified at the specific parameter values. It's not a density in the parameter values, but assuming these specific values, you get a distribution of data. What do we want if we want to do physical inference on particular parameters? Well, if we want to know a temperature of a plasma, for example, and we want to say, then we want to say it's between 2 million and 3 million Kelvin with 90% probability, right? We want to make some statements like that. We already know that the probability of it having an exact value is basically 0 because it's very likely not that particular value, but something slightly different. So making statements about ranges makes much more sense. And so we want a probability density. We want to say something where the probability is concentrated in some particular region. So for infinitely small regions, the probability would then be 0, and that's okay. And so we need, what we actually want is the probability of some parameters given the data. And you know this from yesterday. What I want to emphasize here is that we need this volume of the parameters. And now you can do two things. Either you increase, so you know this is the posterior. And there are two ways to maximize the posterior now. One obvious way, and the way you usually go about it, is you maximize the likelihood, because that will directly increase your posterior value. But you should also keep in mind that there's a volume effect going on here. And that volume is called the prior. So the metric of integration, the volume assigned to a particular way of integrating or measuring these probability densities, you cannot get around that, because we want to make statements about probability densities, and the likelihoods are not densities, and the densities are donated by the priors. So now the next section I would be talking about would be about parameter space exploration algorithms. So how to vary or how to find these regions with high posterior probability or high likelihood, and how to basically come to those constraints on those physical parameters. But before I come to that, I think what we're going to do is, first I'll take questions, and then I will let you go and play with Sherpa and go through the example, because that will allow you to vary one particular model with one particular response. You could do a bit of plotting, and you can vary this likelihood. You can look at the C-stat statistic, which is what I just said is the -2 log of the Poisson likelihood. And you can see how that likelihood changes with changes in the parameter values. So, this will be fairly pedestrian in the sense that you will make these modifications by hand. So this is before you do any fitting algorithms. Okay, but let me stop here and take any questions you have. I'm sure many of these topics were quite new for quite a few of you. So I'm happy to go back and reiterate on some of the points. So either type in the chat or just shout out any questions you have. Okay, don't be too shy, but there will be more time later as well. Okay, so I would suggest then that you go through.
There is a question on the chat.
Okay, sorry. Will we have the slides? Yes, of course. The slides will be available to you. Yeah, I will, at the end, I will also point out a couple of links that you can have a look at if you're interested in more details about how the detectors work, how the mirrors work, some more details on, on various things. There are some links I can share. There's also a longer 2-day workshop that has been video recorded if you want to go into more details that I'm not covering in this workshop. Any more questions? Everyone equally confused? Good. Okay, then let me, oh yes, yes, this is a very good question. Could one photon saturate the CCD? Could one photon saturate the CCD? So, I mean, it depends very much on what type of CCDs you use, and there are various quite diverse types of CCDs. So I'm sure there are some where this happens. One important effect, and maybe I should have talked about that a bit more in this image, is, okay, so here you have a very bright star that's bright in the optical. In the X-ray image, you see that star as well, but you see it because of its optical emission going through the detector and shining on the CCD, which is, again, it's just a CCD, so it also is sensitive to some degree to the optical emission. And you don't want that. Now, what you can do is, of course, you try to coat the mirror to get rid of that. But what can happen both in this, what you see here, but also in bright X-ray sources, is that you get a lot of photons at the same time, because the source is so bright. Maybe I can, where can I show that? Yeah, maybe here. So you have not just one photon coming in, making an electron cloud, and you read that out. But you have, before you can read out, you have several photons coming in and depositing their energy. And now you don't know anymore what was how to make that decomposition into the multiple photons. And that's called pileup. And so you want actually CCDs that read out very, very quickly. In some of the new missions, the readout is milliseconds. So it's really quite astonishing how quickly these CCDs can be read out. But you need that if you want to identify each individual event, and that can be a problem, the pileup in very bright sources. Okay, any more?
So, but may I? So, can you hear me?
Yes.
Okay. So, so in comparison, for example, an optical CCD does not need to be so fast, right? Like.
Yes.
So if.
In the
Sorry.
optical CCD, you basically accumulate all the emission, and then you just make a statement. The total emission in this image was this over this time, because you basically observe photometrically, right? You just have one energy. Yeah. But here we observe many energies at the same time, and we need to know which energy contributed here.
Yeah, this is very interesting. And what about, I mean, if to my understanding, when you showed that grades, okay, so you said that in an experiment one can reconstruct if it's an X-ray or a particle that passed. Did I understand correctly?
Yes, so actually you see that in this image, for example, here and here also, these are particles, protons that, for example, that have much more energy, and they ionize a whole bunch of CCD pixels, and so then you can know that they are much more extended and don't just have 1, 2, 3, 4 pixels being affected.
I see. So it's you have this geometrical information. And what about if it passes like, how can I say, like perpendicular to the detector, like
Perpendicular. Oh, this way.
Yeah, I don't know if.
I mean, you try to shield your experiments to some degree. Yeah, you probably can't perfectly take into account, I mean, resolve that. Although probably can have a look at this again. I mean, even here you see that it ionizes several pixels in the other direction as well, right? So even if it's anyway, probably you wouldn't get a single grade event. And if you really want just a highest quality, you would go for only select these events and discard the more complicated ones.
Cool. Okay, thank you.
More questions? Okay, then I would ask Helen to put us, while people are trickling back, I'll just briefly mention the packages that exist, or some of the important packages that exist. So there's xspec, which is produced by NASA, sherpa, which is produced by the Chandra X-ray Center. xspec has a Python interface, but it's mostly an interactive tool. That's quite old school and very widely used, and most of the models are submitted to xspec and then reused in the other packages. Sherpa is written in Python. It's quite nice to program it. Then there's ISIS, which is written in slang, which nobody uses, that language. But they are very good at taking care of the statistics and doing careful analysis. So it's a very good environment for that. Then there's SPECS, which is mostly used for very high resolution X-ray astronomy. So for example, gratings, which I haven't touched on. So if you want to do ionized winds and stuff like that. And then there's 3ML, which is rather new. That's written in Python, and it's an international collaboration for multi-messenger astronomy. So if you want to combine, I don't know, Cherenkov telescopes with LIGO detections and Fermi or gamma rays and stuff, then this is a good way to combine very diverse instruments together. But the point is you can do good or bad analysis with any of them, and I'll just try to make you understand what you're doing and assuming, and just have to be aware. Okay, so now everyone's back, I think. And I know it didn't work for everyone, and that's sort of expected because we're using packages from someone else that I didn't develop, and very diverse environments. So I'll just give you a brief run through what you should have seen. And where did I have my terminal? Oh, yeah, it was this one. So here I have just a normal terminal. I load chow, which I've installed here. You might do conda activate or something like that. Then I run sherpa, which is really just IPython with some commands preloaded. And now I load my example file. And it already recognized that this response belongs to it. And now I can do plot of the data. Okay. Now I'm gonna set the statistic to cstat, which also changes the error bars a little bit. So now we're using Poisson statistics. Now I'm gonna set a model, which is my power law. So this makes takes an xspec model, which is called power law. You can also just write power law in this case. And I'm gonna give it a name. Just gonna call it my pow. Set that model. Here's the model convolved with the response. You see it doesn't look like a power law. So if I plot the source model, this looks like a power law. Okay, now we can overlay the model and the data with plot fit. Data well below here, and here's the model. So now we're gonna have a look at this thing. Print this thing. This thing has two parameters, the photon index and the normalization. And now we're gonna set the normalization to some value, plot the fit. Now it looks a little bit closer. Now we can do also calcstat, which gives us the value of the statistic. So that's 9,000 at the moment. Let's try to adapt it a little bit more. So we do my pow photon index. Photon index 2. Do calcstat again. Ooh, it jumped up. So this is the likelihood went down. This cstat went up. Oh, yeah, and it's way up here. So it's a worse fit. Now we can go back to, I don't know, 0.5.
Johan, there's a question in chat about some from Matilda saying,
thanks.
So does it not work in xspec?
Oh, it does work. The commands are just slightly different, but the concepts are the same. I can maybe give a brief tour with xspec just after this. And okay, so vary this a bit more, maybe go down a little bit. Oh, it got worse. Oh, it got even worse. Yep, that's again better. So you see how we can modify these parameters and get different likelihood values, which is really just then this would be the likelihood compared to this statistic value. If you want to do the same in xspec, you have to load your xspec stuff. And then I think from xspec import everything. We made a spectrum. That's loading the spectrum. We make a model, just the power law. We do, what do we do? We say fit. Statistic. Oh, that's the current value. Stat method. At the moment is chi-square. We want cstat. And now we say, so this is our model. And then we say we want our normalization to be 10 to the minus 4. and the power photon index to be 0.5. And then we get the fit statistic, and here it is, right? You see it's pretty much the same value as in the other, and you can modify again your parameters and look at the statistic and how it varies. Yes, so now we can also find the best fit with fit perform, or here with fit. And then it reports back these are the best fit parameters, which just means the maximum likelihood parameters, right? Now we can plot this fit. And this is, I mean, we didn't make any cuts in energy. I mean, it doesn't make much sense because up here it's really, these are not focused X-rays. You probably want to cut somewhere here. But you already see, okay, that it doesn't really overlap. And the other thing I wanted to point out is if you modify, let's say, now the fit statistic is this value, 2,448. Now if we modify this to 3.3, changed a little bit. Changed a little bit more. So we varied here by quite a small factor from this to this by about, I don't know, 10% or something like that. But if you look at the fit statistic, originally it was 2,448. And now it changed to this value, right? And now keep in mind, we're working in -2 times the logarithm. And so it changed from by 10, right? So that's e to the 10. Your likelihood changed by e to the 10. This difference, we take the exponential here. Okay. It changed by 4 orders of magnitude. That's how much your probability changed, even though you changed the normalization very little. And the takeaway here is that's because the model is very bad fit. So very small changes in the parameters will drive you very quickly away from the best fit because your best fit is very poor. You kind of you underfitted because the data not as well described by this particular model. Okay, I'm sure that was very confusing. So you have time for questions now. I think we'll have, let's say, 5 minutes for questions. And then I think we'll have a break. And then I will talk about these algorithms which automate the step of changing the parameters and finding best fits for you. Is that okay, Johannes?
Yeah, that's fine. That's great.
Okay. Questions, please.
So is there a way to choose wisely like a model. I mean, or one just have to have a look at many data sets and just like develop an intuition about what could be the best model to try out with a specific set of data, or
Yes, so let me just so one motivation for choosing models can be, of course, the physics of the object that you're interested in. So if you know you are pointing to an AGN, you might choose models that are valid for your science question that have been previously used. You can also look at the data, and that will give you some ideas. So let me just delete the model here. And then if we ignore everything from 0.5, no, from nothing to 0.5 kV and from 8 to infinity. Now we're zeroing in on that. Now you can see a bit better what's going on here.
yeah.
And so you might want to choose something that rises, but then drops at the lower energies. And that can give you an idea of what model you want to use. And if you, I mean, I'm picking here from the model, from the demos that are in BXA. So if you, doesn't matter if you go in the xspec or sherpa examples, the demo is the same. Let's go for sherpa right now. There are these examples simplest, and then where's the other one? Well, let's look in xspec for a second because I'm more familiar with that one. So there are these three examples.
Yeah.
And this one uses a power law model. This one uses a power law and photoelectric absorption, which cuts off the lower energy part, so it makes a decrease here. And then there's a third model which adds a line here. Then the example also uses this model comparison script to do model comparison between those three. That will be the Bayesian model comparison I'll talk about later. So these are three scripts with three different models and model comparison code. They do parameter estimation under each model. And then you have an example here that demos how to do this model comparison. And the same scripts exist for xspec and sherpa. We'll go into that a bit later. More questions? Okay, yeah, so when I try loading the file with xspec, it says it cannot read the response file. You have to download the response file in the directory that you're working in. Okay. Do you want to either share, do you want to share your screen? And in the meantime, other people can think of questions. I need to run Python xspec in the same directory as the data. Yes. Yeah, it's relatively stupid. So in the fits file that you're loading, okay, I'll show you. So here I loaded the FITS file that has the spectrum. It has a keyword that tells it what's the file name of the response file. And usually you shouldn't have any paths, so everything has to be in the same directory and you have to operate in the same directory. Okay, more questions? Okay, if there are no further questions right now, I think we'll go into the break and continue later. Oh, there's something in the chat. It finally worked. Good. And we continue in the afternoon session. I'll talk more about the fitting algorithms. We'll have another demo